All right, so today's lesson, it's called dividing with radicals. We've done adding, subtracting, we've done multiplying. It's time to talk about dividing, but really what we're talking about with dividing is when we end up with division in our answer, how do we make sure it's simplified? And there's like a subheading here that I want you to add called rationalizing the denominator. Because we will need to do that. Now, denominator we know is the bottom of a fraction. Rationalizing is to make rational. Okay? So rationalizing is to make rational. Right? So if it's not rational, we're trying to make it rational. Okay. All right, but first let's look at our warm-up. These are 3 skills we will need in order to do what we need to do today, in order to rationalize the denominator. Okay, so first up, can I simplify this? Well, there's a couple ways. Can somebody give me a method they used? Yeah.
I just turned it to a big.
Yeah, I would too, because I see 8 goes into 24, right? So go on, continue.
You do cubes, giant root, and then 8 over 24.
And that reduces to?
1/3.
Yep. And then you can kind of break it back apart.
Yeah.
Yeah, so now it's the third root of 1 over the third root of 3, because you can do the third root of 1, which is what? 1. 1 times 1 times 1 is 1. So this becomes 1 over the third root of 3. Done it? Right. Like it's done, right? No, because our denominator has an irrational number in it. And we'll talk about how to get rid of that. Okay? So far, all I want you to know is this is not fully simplified. And we'll come back to it. Okay? We would want to continue this and rationalize that denominator. Get that radical out of there. Remember how with like negative exponents, it's like we don't leave negative exponents in our answer. Well, same thing. We don't leave radicals in the denominator. Somebody decided that at one point. They don't like it. I'm sure they had a good reason. So we're not going to do it. So we're going to move them. So we need some skills to move them. So let's talk about how to go from irrational numbers to rational numbers. Right? Because let's say I have this. This is what type of number?
Irrational.
It's an irrational number. And this is what type of number?
Rational.
A rational number. So whatever this blank spot is in the middle must get us from irrational to rational, right? It must accomplish that goal. What is that blank spot? Yeah.
You would do square root of 2, because then when you would multiply it, it would give you square root of 12, which then equals 6. Wait, no.
Close.
That was wrong.
That's okay. It's
My
okay.
brain.
You're on the right track because you were thinking I just need to get down to 6. Square root of 6. Yep. Square root of 6, because that's 2 ways to think about it. You can just remember anytime you multiply by a square root by itself, it's just the number underneath. Or you can think, hey, that's the square root of 36, which is 6, right? So you've rationalized the situation, right? This goes from this situation to this situation, okay? It's one way to rationalize things, okay? Here's the problem, though. What if I had, like, I don't know, 2 minus square root of 6? And I wanted to multiply that by something to get it to be a rational situation. Well, if I just multiply it by square root of 6, I would, yeah, it would like, so this, all I had to do is multiply by itself, right? But if I go by square root of 6 here, this would certainly cancel out, but I would then just kind of move the square root of 6. Like this would be 6, great. but I just kind of moved the square root of 6. So I need something else when I have this, and that's what the next one's about. Okay.
Have to separate it, right?
Well, what you would do is do this. What's the difference between, like, let's say I started with this, and I want to get rid of my radical, and I would do that.
You would do the opposite.
The opposite. So does anyone know what that's called? These are what's called conjugate pairs. So conjugate pairs. So a conjugate pair, I'll go CP for short, is the same term in two binomials with opposite signs. And we've seen this before. Okay? I'm going to put off that example for a second. X minus 4 and x plus 4. Anybody know what that's the result of? When did we get x minus 4, x plus 4, or x minus 2, x plus 2? Yeah, a difference of perfect squares, right? So if we FOILed this, well, it would be x squared plus 4x minus 4x minus 16, which is just x squared minus 16. What happened?
Because those two cancel.
These cancel. Now, that is something we can use to our advantage, right? Because that means anytime you have conjugate pairs, anytime you have the same terms in two binomials with opposite signs, what happens? Yeah, so your FOIL becomes fl, right? You get rid of the oi, just fl, which is actually kind of nice, right? Let's prove it again. Ready? If I FOIL this, right? Well, that's 3 times 3. That's 9. Whoa, turned into an arrow. 9. 3 times negative square root of 2. That's minus 3 square root of 2. 3 times positive square root of 2. That's positive 3 square root of 2. And then square root of 2 times negative square root of 2. Positive times a negative is a negative. Square root of 2 times square root of 2 is 2. And boom, 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 boom. Get rid of those, and I just have 9 minus 2, which is 7. And once again, we started with irrational. And now we are rational. Okay, so if we have something like this, and we multiply it by its conjugate pair, we get to a rational result, right? We get to 7. Whoa. Okay? So, FOIL becomes just FLA, right? I don't even need to really do this middle part anymore if I know I have a conjugate pair. Just do first, just do last, right? I'll show you examples, okay? Okay, so those are our two ways to rationalize situations, right? Either just multiply by the root that you have or the conjugate pair. All right, so when would you have to do that? Okay, so, actually, first let's talk about why we would have to do that. Okay, so here's the rule, right? I'll give you the rule through an example. 1 over the square root of 2 is not simplified because square root of 2 is irrational. And you need to rationalize the denominator. To fully simplify. Okay? So, for all the problems today, I want you to pretend like you've done like a problem, like you're solving or you're doing simplification, and you get to this as like your final piece. I brought it all together. Maybe I was adding or subtracting. Maybe I was multiplying. And I got this, right? And I'm about to walk away, and then I go, wait a minute. I see a radical in the denominator, right? So it's like the extra piece that you need to do before you walk away, okay? Well, we know if we need this bottom part, the denominator, to be rational, and right now it's irrational, well, now we know how to fix it, right? What would I need to multiply this by to make it rational? Square root of 2. And I can't just multiply the bottom by something. I have to multiply the top, right? It's that simple. So I get 5 square root of 2 over 2. And that's considered more simplified than that, okay? So don't leave it like that. Move it to that, okay? Now, obviously it can get a little more complicated than that. You might end up with this as your final answer and think, I'm good, but you're not really, because this could be rewritten as square root of 6 over square root of 5, and if it could be rewritten with a radical in the denominator, it's just as bad as if you have one, right? So you have to fix that as well. So you would multiply this by square root of 5, square root of 5, right?
But then you can simplify it at the top.
Sometimes you can, sometimes you can't. This would be square root of 30 over 5. Maybe at that, you've hit on something. Maybe at that point, oh, now I can simplify the top and keep going further. Maybe you can't. Like, square root of 30 does not break down, right? It's just like 2, 3, and 5. It doesn't, there's nothing you can simplify that to. So you're done.
I got confused because I was thinking about the addition of the
Oh, okay. Gotcha.
multiplying.
Now, I want you to try these two, and keep in mind what you just talked about. Like, maybe after you do it, you might have to simplify further, okay? So try these two. Then we'll go over the conjugate pair version of this, and then that's it. That's the whole lesson, okay? Question? So go through these real quick. What would I multiply this by to rationalize the denominator?
Square root of 5.
Square root of 5 and square root of 5, which gives me,
20 square root of 5 over 5.
over 5. So is it fully simplified? No, because why? 20 divided by 5 you can do. If you can do it, you do it, right? So this becomes 4 square root of 5. Okay? So sometimes what you do creates another step. Okay? Over here, I end up with square root of 40 over square root of 3. Now, at this point, you might think, sweet, square root of 3 over square root of 3. However, you might want to simplify the top first, because if you multiply that by square root of 3, you're going to bump it up to 120, and then you'd have to simplify that, and that's a much bigger thing to simplify than square root of 40. Square root of 40 might be pretty clear to you what to do, right? Because square root of 40, well, that's 4 times 10, right? And that's 2 square root of 10. Like, it might not be as clear when you get to 120, right? I don't know. So this, square root of 40, becomes 2 square root of 10 over square root of 3. Now let's multiply by square root of 3 over square root of 3. And I get 2 square root of 30 over 3. And we already talked about 30. You can't break down 30. All right, so that's one version of this. The other version is working with conjugate pairs. So you must use conjugate pairs in order to fully get rid of this radical. Remember we talked about, if I just multiply this by square root of 2, I'm just moving around the square root of 2. It's not going to go away, right? I can't just do square root of 2 over square root of 2. I need to multiply by the conjugate pair. So, big old line, right? And what's the conjugate pair of 3 plus square root of 2?
3 minus 1.
Exactly. 3 minus square root of 2. 3 minus square root of 2. And then the very last thing you will do is you will put parentheses around everything. So you remember, you remember that this is a binomial times a binomial. This is a number that must distribute, right? Because what you end up with is 4 times 3 minus square root of 2 over 3 plus square root of 2 times 3 minus square root of 2, right? Both of those, you could rush and just multiply the first thing if you don't realize you got parentheses there, okay? Now, what happens? Well, on the top we distribute, right? 12 minus 4 square root of 2. And on the bottom, well, since we know we have conjugate pairs, we can just fluff. Forget the oi, right? 3 plus, 3 minus. It's kind of messed up my 3 there. Come on. Right? So I would just say first, well, that's 9. And then last. Square root of 2 times minus square root of 2 is? Minus 2. And I don't really need to worry about the middle 2. Right? Conjugate pairs. So this is 12 minus 4 square root of 2 over 7. And yes, that is considered more simple than what we started with.
Do we have to break it down even further?
Well, you might, but you can't divide those by 7.
Yeah.
But you might. If it was 2, you would.
I mean, like the 12 minus 4.
No, because you could factor out a 4 there, but of course you could, because that's what we multiplied through by.
No,
That's going to happen a lot, yeah.
I mean, like 12 minus 4 just as together.
No, because that's like having 12. That's like if you had 12 minus 4x. Would you do anything with that?
Oh, okay, that makes sense.
You wouldn't bring those together. Question.
How did you get 12 minus 4 square root of 2?
Well, we multiplied 4 times 3 minus square root of 2. So we distributed that 4, which gives us 12 minus 4 square root of 2. Okay, just distribute that through. All right, one more, and then you can practice, and then give you your homework. All right, so sometimes you have a radical up top. It's okay. You can distribute a radical, right? What's my conjugate pair? 1 plus square root of 3. 1 plus square root of 3. It's just because you have a radical doesn't mean you can't distribute. Doesn't mean you shouldn't distribute. So this distributes through just like a number would, right? And you end up with square root of 2 plus square root of 6, because that's square root of 2 times square root of 3, right? And on the bottom, well, it's fla, right? So that's 1 times 1, which is 1, minus square root of 3 times square root of 3, which is 3. So square root of 2 plus square root of 6 over minus 2. And that is done. Okay? Now, I will say on your homework, the answer key, they like to move the negative up top. So they pull the negative. They like the negative in the numerator. So they just make this positive and flip all the signs up there. If you see that, that's all they're doing. I don't expect you to do that. Okay.
Does that mean that we would have to simplify again because it's a radical?
Well, there's nothing that can be combined here because these are different radicands.
No, I mean like, so you said that the negative would go up on the
Oh, all I'm saying is that the homework will say, okay, well, a negative can come out front and be square root of 2 plus square root of 6 over 2. And then they distribute it through the top.
Okay, that makes more sense.
But you don't need to do that. All right. Go ahead and try these problems, and I'll hand out your homework and your review, and you're done. And then if you have questions, let me know. This one would be 10 minus 5 square root of 7 over negative 3. Or maybe if they moved it up top, it would be different. And this one would be 5 square root of 6 plus 6 over 19. Okay? Okay. Homework was all about adding and subtracting radical expressions, right? So that is roots and radicands, right? And you needed both to be the same in order to bring them together. You need the same root, you need the same radicand. Radicand is another word for the base, right? So root, radicand, right? You need that same thing, and then they're like terms, then you can add them together, just like if they were x and x, right? 3x plus 2x is 5x. Well, 3 square root of 2 plus 5 square root of 2 is 7 square root of 2, right? Just think of them as that. Now, sometimes they were hidden, right? Like sometimes you look at them and you're like, oh, those aren't the same radicand, but it's because they're not simplified. So you have to simplify them first, then they reveal themselves to be the same, right? So that's the extra challenge on some of these. These are kind of all over the place on the homework, so I will just kind of circle the ones we want to do, and then we'll go through them. So which problems would you like to see? 2. That makes 3 for 3 on classes with number 2. Next. What else? 5. Okay.
And we're just talking about the front, right?
Well, for now, I'll circle the front, then we'll go to the back. Number 6, we'll talk about. Okay, anything on the back? Well, 11? 10, 11. All right, we might not need to do all these if some of these are similar. Maybe we'll go through one and it'll make the other one make sense. But I think we got a good starting point here. Number 9. All right. So I know nobody asked about number 1, but number 1 is a very great example of what we're doing here and its simplest form, right? You got square root of 6, square root of 6. So that's second root, 6, 6, same root, same radicand. So it's almost like you have 2x plus 3x, which is 5x, right? Well, in this case, the x is square root of 6, so it's 5 square root of 6. That's what we're doing, right? That's the easiest version of this. Now, number 2. Well, you're doing your mental checks. You're like, all right, same root, 3 and 3. Okay, we're good there. And then you go to check the base, and you're like, 5, negative 5. Yeah.
Well, if you multiply the negative that's on the outside.
Kinda. Yes, but there's more to it than that. Why are you allowed to do that? Because it's not like if it was the square root of a negative, I could do that. It's a cube root of a negative, right? A cube root of a negative. There's basically, the rule is the third root of negative 5 is equal to negative third root of 5. Okay, that's a rule you can remember. You can always pull a negative out of an odd root. The reason is, if you pull this apart, it's the third root of 5 times the third root of negative 1. The third root of negative 1 you can do. It is negative 1. Negative 1 times negative 1 times negative 1, right? So that's negative third root of 5, right? So you can do that, okay? So suddenly this becomes like terms if you say this is 3 third root of 5 minus third root of 5, right? Or minus 1 third root of 5. Minus becomes a plus, and you have 3 third root of 5 plus third root of 5, or 4 third root of 5, right? A little bit of a trick there. I would say I wouldn't put something that tricky or devious on a test, but if you got it, you can feel good. Like I noticed it. I noticed the little trick. Okay? All right, so that one was kind of a unique one. All right. Moving along, the next one we wanted to see was 5. Well, 5, there's two ways you could do this. You notice that they left their answer in exponent form, right? We were dealing with radical form. But if you had like 3x squared plus 7x squared, you would say that's what? 10x squared, right? Well, it's the same thing. It's just you have a weirder exponent, right? This is 10x to the 1/3. Now, you could have also, since the rest of them are radicals, maybe you felt like I needed to make this a radical. Well, if you did, it would be 10 third root of x. Okay? All right, moving along. This one. Now, you'll notice the answer is the same as the question. That's because you can't simplify it any further, right? Well, you do your little check. You're like, all right, the base is the same. My radicand is the same. But if I put a little root here, I got a 2 and a 3, and that is not the same. So they're not like terms. You can't bring them together. Okay? All right, moving to the back. All right, number 9. Okay, so at first glance, you would say, well, they're both square roots, right? 2 and 2, which is good. But these two numbers are not the same. However, you always have to simplify before you do your final check of whether they are like terms, right? So you would do them one at a time. You would say minus 3 square root of 27. You could jailbreak that, or you could try to find a perfect square inside of it. Perfect square inside of 27 would be 9, right? So this is minus 3 square root of 9 square root of 3. And square root of 9 is 3, so that's minus 3 times square root of 3, or minus 9 square root of 3. So this becomes this, and you can replace it. So you would say minus 9 square root of 3, and then minus, okay, now let's take a look at square root of 12. And I try to find the square root inside of that. Or I try to jailbreak it, and I find out I got square root of 4 times square root of 3, right? Square root of 4 is 2, so this is 2 square root of 3. So then this becomes this, and you can replace that, which gives you minus 9 square root of 3 minus 2 square root of 3. It's like having minus 9x minus 2x. Well, that's minus 11, and then your thing. Minus 11 square root of 3, and that was your answer. You also could have jailbreak in both of those, where you break it down all the way, and because it's a square root, you'd look for pairs, groups of 2. Okay? All right. Number 10 is quite similar. You would need to simplify both of those. This would break down into third roots, where you get down to a third root of 3, third root of 3. I will go over this one just so I can show the jailbreak, right? The different methods. So first, I have 2 third root of 24. Well, 24 broken down, that's 2 and 12, 2 and 6, 2 and 3, right? Throw that all back under and look for a group of 3. So that's 2 third root of 2 times 2 times 2 times 3. Looking for a group of 3 because it's a third root, right? And I see they have 3 2's right here. So one will come out here, the others go away, and I end up with 2 times 2 third root of 3, or 4 third root of 3. Okay? So that's going to go in place of this, and I have 4 third root of 3. Minus, now I got to take a look at the other one. So I got 3 third root of 81. Well, let's break down 81. 81, I'm going to do this, instead of dividing by 3, divide by 3, divide by 3. I know it goes in 81. 9 goes in 81. So I can just do it that way. Like, there's no reason you can't start with whatever number you know. 9 becomes 3, 3, 3, 3. Right? you still get to your numbers, okay? So this becomes the 3 times the third root of 3 times 3 times 3 times 3. I'm again looking for that group of 3. Here they are. One comes out, the others go away. And I am left with 3 times 3, third root of 3. That's a lot of 3 threes. That's 9 cube root of 3. So that goes here, right? So I have 9 third root of 3. 4 third root of 3 minus 9 third root of 3 is minus 5 third root of 3, okay? Just like it would 4x minus 9x would be negative 5x. Like, think of that in your head if you need to. So this is minus 5 third root of 3, okay? All right, I think we got one more. All right, here, well, first I would check at what's even close, right? This one is a third root, and then I have a square root and a square root. So the only ones that are very even possible to bring together are going to be these two, right? So I'll take a look at those in a second. But it does say fully simplify, so I still got to simplify this one, and I won't go through that because that's just jailbreaking or breaking down. But the third root of 48 becomes 2 third root of 6, okay, if you simplify it. Over here, I would do the same thing I just did with these other two, and I would end up with, and again, I'm going to skip a little bit. This will become square root, right? So this will become minus 9 square root of 2, this one. And this one will become minus 6 square root of 2, right? If you do the jailbreak or you do the simplification. Minus 9 minus 6 is minus 15, and then that gives you your answer, okay? Kind of jump through that one because we've done very similar ones already. All right? Okay, on to the lesson. So in today's lesson, boom, boom, boom.